This particular session is about Spring-driven industrial IoT, the extra I in IoT. And what we're going to talk about is how we can use Spring, Cloud Foundry, and GemFire to significantly enhance industrial processes. Things like assembly line construction, power plant control, things like that. And what we're going to go through, we're unable to bring in a petrochemical power plant today, so Barry was nice enough to put together this eensy-teensy tiny little demo for us. And on this demo, you're going to see a lot of things very, very familiar to industrial processes. There's going to be on here programmable logic controllers. There's field bus for communications, power supplies, a lot of cable, and probably the most important thing is this little red do not panic button, just in case. So one thing that I noticed in a lot of the sessions over the last few days is that there's a lot of discussion around digital transformation. And we are very honored to be able to work with our customers on culture changes, process changes. When we talk about this is going back to the original digital transformation, digital to analog, analog back to digital to be specific. So my name's Mark Weislow. I'm the engagement director for Pivotal, and I'm co-speaking with Barry Wood. Barry Wood is with RPY Motion, and he's a very good partner of Pivotal's. And we'll go ahead and dive right in. So what we're going to do today is talk about industrial components. We're going to talk about how we use the components and how this open source solution gateway can be used to enhance the whole digital process and control process within power plants and assembly lines and things like that. And we'll go into details of additional use cases that we can use as well. So the story for today, imagine, if you will, drones. And as I was preparing for today's presentation, I found a couple of things that were a little bit counterintuitive. The first one is that if you look at the auto industry, they're primarily driven by combustion engines today, and now there's a resurgence into hybrids and electric engines for autos. Within the drone industry, it's almost taking the reverse of that, because drones primarily are driven by electrical motors and batteries. But with some of the current needs of things like delivering heavy packages to houses by retail stores, doing long-term flights, surveilling construction sites and underneath bridges looking for faults, we need drones that have a little bit more power. So we're talking about the movement from electrical power back to combustion engine for drones. Because if you look at batteries are very unfavorable when you talk about the power to weight ratio, where liquid fuels are much, much better. So drones can be in the airs much longer. They can carry heavier workloads and things like that. So in our story, what we're going to be showing is how we can do things like making sure that we have exact custom parts. In this particular example, with our combustion engine drones, we're going to be showing the example of pistons and cylinders. The second somewhat counterintuitive thing that I learned is that there is a significant leap in productivity of constructing things when we had interchangeable parts and the assembly line. Here, we're going to take a little bit of a reverse on that and going back to custom parts where you have to have exact pairs. And that's the need based on things like customers wanting things to be very custom today. So we're not going to build millions of one thing, but we may build smaller amounts, so we have to make every part count. So that combination of the customization of parts, as well as keeping low margin for competition, so we need to keep the cost down. We can't afford to throw away parts. So in our example, we're going to have one vendor who bores the cylinders in the engine blocks and ship that out for assembly. We'll have our second vendor actually making the pistons. So the second vendor is going to have to know the exact size within tolerance that we can make those pistons. Okay. So the focus for today, we're going to talk about how we can use Spring, Cloud Foundry, and GemFire to significantly increase the use of, or the functionality of current industrial processes. So as a quick overview of the processes, really this is what you'll see typically out there in the environment. At the high level, you have something called SCADA. And SCADA is really software that's used to drive, or think of it as like mission control of controlling industrial processes. And the thing you see right above SCADA to the left is that HMI, human machine interface. That's where currently you can push buttons that say, turn on this water pump, turn off this water pump, make sure the coolant is at the right temperature and things like that. That then typically will talk to one or a series of PLCs, Programmable Logic Controllers, usually in the hundreds or thousands. And they're really the interface between the humans working on the machines at the upper level within the enterprise and the communications down to the device level. So the PLC is really like a ruggedized computer with some minimal functionality to run things like stored procedures that will control the devices. The devices will be communicating with PLCs, engines, lasers, things like that, through various different field buses. And the lower section there in that nice pivotal green color is left blank for the moment. That's to build the anticipation on what the solution is going to look like, which we'll get to shortly. So just a little bit more detail on SCADA. So SCADA is a supervisory control and data acquisition. And SCADA is all about controlling devices at the enterprise level, really, usually remote from the devices themselves. And they're typically used to control the devices, alarm response if things overheat. Besides the device having safety features itself, we want to make sure there's redundancy. So they will have alarms which can immediately notify individuals and turn off certain devices. And they capture data for analysis, so it's really two-way communications. Typical programming of SCADA environments is C++ and fourth-generation languages. The PLCs, the Programmable Logic Controllers, they're the interface that goes to the device themselves. They'll control things like the motion, the speed, the torque, things like that. They're very good at reading inputs, executing basic logic, and then writing outputs back as sensors back to SCADA or back to the enterprise for analytics. And there will also be things like PLC to PLC communications for redundancy and for high availability to make sure that devices always are under control and don't go running amok themselves. There are various different languages that can be used by PLCs listed here. The only other thing I'll say about the PLCs is that really their predecessor, what came before them, was electromagnetic relays. And the relays were always very hard to reprogram. So when you're talking about conveyor belts in a food industry or things like that, there had to be a move from relays to something much more easily to customize and change out processes, which is why PLCs were invented. Okay, so I'll fill in that little section now just a little bit. So besides SCADA, working with programmable logic controllers and other things like RTUs, which are remote terminal units and distributed control units, what we're going to propose today is that by using Spring projects, GemFire, and Cloud Foundry, you could significantly enhance through this gateway the capabilities of SCADA and the capabilities of programmable logic controllers so that you can speak with and control devices that aren't necessarily compatible with what might be a proprietary SCADA system. Okay. Where does that fit in a typical IoT layer? Arguably, you could say that at the cloud computing layer, there's a lot of vendors out there that make IoT libraries available to you. But there are some issues of the cloud environment directly controlling devices themselves. So what we want to do is we want to try to drive the computing as close to the physical devices as possible. So that way we don't have to worry about latency issues, bad connectivity, and pirates out there trying to steal the data from the devices themselves. So that first layer that we have is closest to the devices is the edge computing layer. And that's where we have real-time control of the devices. We have things like the PLCs that I talked about briefly. There's microcontrollers out there. There's a lot of research going on now and some great new things. There's something called a Pi board where you can run MicroPython to control devices themselves. So that way you can actually have a microcontrolling unit directly attached to the device itself so the device can do analytics at that level. Going up to the fog computing layer in the middle, that's where you can have near real-time data connectivity with the devices. And you can do things like group-level analytics. You can scan across a series of devices so that you can do analytics and trends based on groups of devices. You could also do aggregation, because at this point, if we're talking about hundreds of thousands or millions of devices out there, we don't want to saturate our cloud computing environment, so we're going to aggregate data before we send it up to the cloud. And then up in the cloud is where we could do our advanced machine learning algorithms, analytics, and we could build our data-driven organization. Okay. So with that, we're going to dive into a little bit of a detail of this proposed open source gateway. Okay, Barry?
Thank you, Mark. My name is Barry Wood. I'm with RPY Motion, and I work with Pivotal and a lot of facets here. And today we want to talk about connecting to the real physical world. That being the motors that control things, the temperature sensors, flow valves, any kind of physical world. How do we normally connect those two together with the enterprise world? In the past, and even in the current situation we're in right now, there are really two distinct worlds. We have the enterprise world, and then we have the control low level, the factory floor, or even any physical device, even if it's not a factory. If it's a door at a warehouse or something like that, how do you connect to that device so that you can control it? So right now, the current state of things is that we use a very low-level control, as Mark has talked about, where we use PLCs and SCADAs. But they're first of all very heavily proprietary, and they do not connect well into the enterprise environment. So what we're talking about here now is a solution built around using the Spring Integration framework to connect these two distinct worlds, connect the physical world, the plant world, with the enterprise world. And so that's what we're going to be demoing here. This demo is we're not going to be showing a lot of code. I'll make the code available to anyone that wants it. I'll be glad to share it with you. We're going to actually demo, and so that you can see the Spring framework actually being used to perform these tasks. Now, so this slide right here talks about the communications. The real key to this gateway solution is the Spring integration and the communicating from the IoT bridge down to our edge devices. Now, we're using a PLC that is built on an open PLC. It's an open source PLC called Codidus. Codidus is a basic operating system, and it'll allow me to have access to the operating system and open up sockets, which a lot of PLCs, the proprietary PLCs, they will restrict you on that. They will not allow you to have that type of access. So the PLCs we're using here is actually built on Codidus so that we can actually make a physical socket connection. So what we're doing here is in our Spring, this laptop is the bridge. This is the edge device down here. And the PLC is this red device here that we'll be showing here in a few minutes. So what we're doing is communicating, we're using both TCP and UDP communications. And so we are connecting down to the low-level devices. So now down here at the low-level devices, the PLC, what is it going to control? The I/O. And that can be discrete I/O, 24-volt DC. It can be 120-volt, 230-volt. It doesn't matter. We can buy I/O, and if we need to change 5-volt, we can put some optical couplers on it, and we have it covered. And we can control the physical I/O, along with we can control motors, variable frequency drives, servo drives, any type of drives, things that run on field buses. Now, in the physical world, they use a lot of field buses for the communications between the programmable logic controllers and the actual drives and devices. And that's done with things like Profinet, Profibus, DeviceNet, Modicon, EtherCAT, EtherIP, and be aware that EtherIP is not Ethernet TCP. There's a lot of differences there. So they use field buses to communicate with these low-level devices. So what we're doing here is we're using a PLC that we can talk TCP back up to the IoT bridge, and then we can buy this PLC with any field bus on it, Profibus, DeviceNet, so that we can talk to the existing systems. So this is giving us a gateway into existing systems to pass control, along with the factor of we can add in new devices or control any of these devices. So in this solution, we're going to demonstrate the IoT bridge, and we're also going to be demonstrating the use of GemFire as the cache between the isolation level to decouple the IoT bridge and the factory floor from the enterprise. And so GemFire is going to be our decoupling mechanism, and this is also going to allow us to enhance the security of this solution is through the use of GemFire by segregating the low-level world from the high-level world. And we'll be looking and talking about that. So the actual physical demo that we have, you'll see here, is first of all, we are talking from the IoT bridge through Ethernet switch to a PLC, and that's all Ethernet TCP. And then we're using CAN bus, which is a field bus, to talk to the I/O, which then the actual physical world devices are connected to the I/O, and we have both input and output modules on this I/O. Now, we are using two stepper motors to control the position of two disks, and we have closed the position loop with an encoder. Each stepper motor has a quadrature encoder, and that's being fed back to our input devices shown here in the CAN bus I/O and input and output. Our encoder signals are fed back there in red, along with we're outputting the control signals as far as the step pulses, the direction, and the enabling of the stepper drives. That's coming out of the output out of our I/O. And so now this is actually, we are doing positioning control here with this demo, and the control signals are going to come from the IoT bridge, which is a Spring-based application. Okay, so first thing we want to do is I want to get the camera on here.
Okay.
Yeah.
Yep.
Can we make that a little bit bigger for right now?
Yeah,
Yeah, just
absolutely.
for right now, because I want to show the components of what's actually here. Okay. Okay, so this is the actual demo unit. So what we have here is we've got two wheels which are driven by stepper motors that's mounted in the back. And this is our Ethernet switch to our PLC right here. Now, the purple cable is our field I/O bus to our I/O coupler module, and then we have 2 input modules and 1 output module. And all the stuff on the back is nothing but power supplies and circuit breakers that was required. And so we're basically communicating down through this cable from our IoT bridge, which is Spring base, through Ethernet cable to our PLC, and then the PLC is communicating out to the I/O modules through this purple cable, the CAN field bus. So the next thing we're going to do is I'm actually going to do a demo with this, and we're actually going to run it. And what I'm running here is a Spring Boot application with see if we can move this down here so we can get a little better view of the wheels here. Okay, so first thing in any industrial control application, or even if you're controlling doors or anything at the warehouse, you have to give the operator the ability to operate the system manually. They have to be able to take over manual control of the system. So the first thing we're going to demo here is this screen that you see here. This is the HMI that Mark talked about, that a lot of time is associated with the SCADA system. You also, in some industrial applications, use HMIs that are attached directly to PLCs. This particular case, we're running a Spring MVC application here, and this is actually going to be an operator interface that we're actually going to control, turn these things on and off. So the first thing is we're in manual mode here.
Just going to fix this real quick.
Do I need to button my shirt?
Yeah, exactly. Good. Sorry about that. That way we get this. Okay, there we go.
Okay. Thank you. So the first thing we're going to do, we're in manual mode right here. We can switch modes with this button. This section here is control push buttons. They are equivalent to what you would see on an electrical panel that an operator would go up and push, regular type push buttons. So we're going to jog. Okay, so we're jogging. We're going to call this the machine axis and this the rack axis. So we're jogging I clicked on the jogging the machine axis clockwise, and you see the feedback message that we're getting here saying it's jogging clockwise. And I never did a submit. We're using WebSockets here. So if you're going to do any type of HMI for operator for real-time control, you're going to need to use WebSockets because you can't be resubmitting the form. Likewise, we can jog counterclockwise, and we can jog each of the axes. We can jog in both directions here. Now, the next thing we need to think about is with any motion system, we always have to reference the system. We have encoders that provide feedback, so we need to reference the system so it knows what the 0 point is, so that when you tell it to move X amount of distance, it moves it from the correct point. So let's go ahead and reference our system. It says right now axes are not referenced. So both of the axes are going to reference, and you will see it come around, and the two little lines right here line up. And so now our system is referenced, and you see that it says the system is referenced. Another set of functionality a lot of times you need to do manually is move to some fixed position. And so this particular case, we're going to rotate the wheels 180 degrees. That would typically be like on a die cutting press or something like that if you need to move the head so that you can change the dies. This would be an application where you would move the dies to a fixed position. Okay, so the next thing we want to do is we want to run an auto cycle. And Mark was talking about we were manufacturing pistons. And so what has happened is we have a vendor manufacturing cylinders in another location, maybe China. And this is, let's say it's a very low margin product. And we do not want to throw away any cylinders. And the boring operation is always more difficult to hold the tolerance on a bore than it is on a turning operation. So what we're going to do here is we're going to bore the cylinders, and then at some other remote location, we are going to send them the bore diameters, and they are going to then use that information to control their machine to actually produce a part that will match that cylinder. And so what we're showing here is that diameter is in GemFire has been passed down from the enterprise into GemFire, and we're going to pick it up in the IoT Bridge and pass it down to our low-level controller. So like passing it into a CNC machine as a set point for the OD of the turning operation. This is what this is really simulating. But we can't bring in a turning machine, so we're going to do it by moving to different color segments on the disk. So the first thing we're going to do now is run an auto cycle. So I'm going to go ahead and initialize some data up in GemFire because I am not actually connected externally outside here. So what I'm doing, I just loaded some set point data into GemFire. And what we'll do here is let's go look at that data. So here are the set points that we loaded in. We've got our piston ID, and we're specifying the color and the position set points. These position set points are the encoder counts off of the 0 position, is what they are. And this particular encoder has 800 counts per revolution. And then we're going to go in and we're going to move to that color segment, and then we're going to actually make 12 variances, like to simulate the process variance. And we're going to capture those variances, and then we're going to bring those out to the screen, and then we're going to do some simple statistics on it by looking at the average, the min, and the max of those values. And that's going to be done at the IoT Bridge level, and then the results of that will be passed back up to GemFire, which will then be accessible from the enterprise level. So these are our set points that we're going to be running. Okay, so let's go ahead now. First thing we're going to do is go to automatic mode here. Switch to auto. And let's tell it to run a piston. And let's say so we'll run our first piston. Okay, so what it's doing is, and let me go to this other screen over here. So what it's going to do is move to the brown color segment. Okay, now it's going to see it start making movements, and these are the different process variance measurements here that's being displayed here. Okay, the next thing that's going to happen is the rack position that we would place that particular part in, like a pick and place unit or a robot. We've got to command it, so we want these parts in specific racks, so when they show up at final assembly, when the pick and place unit or the robot picks out of cell 1 and the piston out of cell 1 and the cylinder, they are the correct match. So we're simulating here where we're placing these parts in the rack. And so this particular case, our rack position was red. And you'll see that this moved to the red here. So that particular part is complete. So let's go back and run one more, and then let's go look at the data that we actually sent out to GemFire. Okay, so now we're going to be moving to the blue color segment. And now we're going to we've got the simulated process variances, and basically I used a random number generator to generate position offsets from the center of that blue segment. And the rack is going to be moving to the black segment there. So the center point here is between these wheels is actually the correct alignment. So we've now run two parts. Let's go look at the data that was pushed up into GemFire. And so what you see here is, if you look across there, you will see that we have two pistons, piston ID 3 and piston ID 1. And the data, what we saved there was the colors, the position set point, the position colors, and those 12 measurements that we took far as process variance, along with the average, min, max data. That got saved there in GemFire. And what we did, we've got in this particular application, there's two GemFire regions. One for storing the set points, which would be passed down from the enterprise to the IoT bridge. And then the IoT bridge is going to communicate those for each part that gets run. When I basically did the auto start, I was passing down the new set point that would be passed down. And that set point was coming out of the piston set point region out of GemFire. And then when the part completed, after we did the 12 measurements and the rack position, then it saved that data that was on that screen, got pushed up into a region called piston manufacturing data. And then that data could be retrieved by the enterprise system from GemFire. So that is the demo. Is there any questions on the demo? Anybody got anything they'd like me to see me do with it? Well, I'm going to talk a little bit more. I got some other things. I'm just doing the demo right now before I kind of move these screens back out of the way. Okay, let's talk a couple other things we want to talk about here. And let me get the PowerPoint back up.
You just hit the play. Good.
Okay, so let's talk a little bit about how this was actually done. And I forgot to bring my pointer with me. So basically what you see over here on the far upper right, we have the view, and that was a view JSP. And we had a control block box that in their table, and that was our control buttons where we could jog and kick off auto, reference, and that kind of thing. And then we had the status information. And that information, and all of that was being passed back to the controller using WebSockets. We never submitted the form. So the operator never had to go off of the screen to actually perform those operations. And the controller then is updating our model. And to communicate that data from the IoT bridge down to our PLC, we're using the control signals, the jog buttons, the start buttons, and the stop buttons, things like that, are done using TCP because we need to ensure that they arrive, and it's a handshake. We send those signals down from the IoT bridge to the low-level controller, and then the low-level controller turns around and sends them back to the IoT bridge. And that is so that you can verify that they arrive, because in a control application like this, you have to verify that the signals arrived. And the other thing is that some signals are maintained, some signals are one-shot. And so this allows us to handle that appropriately based on the type of signal. And then we, in our transformer, we are taking these objects. We are working up in the IoT bridge in objects, but this controller does not know what an object is. It only knows what bytes are. So you have to convert that object into a byte array. And then that byte array gets communicated down to the controller, which is on the bottom, the PLC to the receive buffer. And then inside of the controller, we have to receive that message. And the very first thing, you have to develop kind of your own protocol with this, because you got to specify for the controller what's the length. So that's the very first field it's going to see is the length. And then go get a message code to tell it what does those bytes mean. And so you will break that down in the controller. And then likewise, you have to build that message back up as a byte array out of the controller to send it back up. And that comes in on the inbound channel, TCP channel. And then that actually gets, in the transformer, we convert that byte array into objects then that can be used inside of the IoT bridge. Now, for updating the status data, we do not have to handshake on that. So we use UDP for that. In this particular case, we are scheduled to send the status data on a given interval. And we're talking about here intervals of 300 microseconds. And we send that up, and that, here again, that byte array is transformed into an object, and that object then we update out of the service activator. We call a listener that will update the model data, and then that model data gets converted into display data and basically strings that then get sent through the WebSockets to update the data on the screen. So how does this solution then fall into, I'm just checking the time here. What is the overall solution then? So let's take a look at this. What we've demonstrated here is on the bottom, starting on the left, the PLC, the Ethernet switch, into the LAN connection, and we're running the Spring integration in MVC. So that's what you saw, the Spring integration with the communications from the IoT Bridge running on my laptop here down to this PLC. And then we're using WebSockets to update the view. And I'm actually, for this particular case, I'm using a Java native client, and we're retrieving data from GemFire. So the IoT Bridge is pulling the data from GemFire and also passing data to GemFire. Now the enterprise will access the data by coming from like Pivotal Cloud Foundry or PWS, AWS, whatever cloud you want to use. You can access the data in GemFire using a RESTful interface. You would typically use a RESTful interface for the enterprise to retrieve the manufactured data along with passing down any kind of set points or control values. Likewise, we could be running other applications here that would communicate with the enterprise, that would pull data from GemFire. Now, I mentioned earlier that GemFire gives us a level of security here. And that is achieved from first of all, GemFire has its own built-in security. So through the GemFire Security Manager, we can authorize and authenticate anyone connecting through the RESTful interface. Along with, we can authenticate the IoT Bridge if we need to. But we also are loosely coupling this because the only connection with the outside enterprise world is through GemFire. The IoT Bridge has no direct connection. It's only connected to the floor level control systems. And this is very important in manufacturing. People are very concerned about people getting access to the low-level controllers. And so we have actually got kind of two levels of security here. So just a quick overview of what we just saw here. I really want to talk about this more from where you can go with this, in that the physical world is heavily built around PLCs and distributed control systems, DCSs, and a lot of that control. And you got to remember, in that world, we talk about milliseconds in control. When we start doing positioning control, you have to run your position control at, if you're synchronizing between axes, typically 1 millisecond. Now, if you start talking about temperature, well, and or flow, you can look at the heat capacity of what you're controlling. Well, you may be able to only need to update that every 10 seconds or 30 seconds may be sufficient. But when you start talking about motion controlling, or typically like in automotive manufacturing, when you're controlling the assembly line, you're talking about milliseconds on that type of control level. So we're not talking here about replacing that. What we're talking about here is connecting that world that right now is kind of a little isolated, and they typically make that connection with the enterprise through SCADAs. But that's a very proprietary environment, and making changes is not something simple that the average enterprise programmers have ever seen. A lot of that code is still C code, and in some cases, we have run some assembler. I have seen some assembler level stuff run in PLCs. A lot of PLC programming is in assembler, and that's just because of sheer speed. So what we're doing is we're giving you a way to use this as a gateway to connect down to this low-level world. And we can have any of the field buses are available on these PLCs so that we can talk through the PLC, and the PLC becomes a gateway. Along with, now we can bring data back up to the IoT bridge. Now, from a data analytics perspective, if you are sending data every 100 milliseconds, do you want to pump all of that up into your enterprise? You may want to do some level of filtering or aggregation on that data to reduce the amount of data that you would pass up to the enterprise. And that's what we saw here when we calculated the average, the min, the max on these. We were actually performing some data aggregation, data filtering. Or you can pass all the real values. I mean, if you got the bandwidth, that's pass, you can pass whatever. And then we can pass up to the cloud, and the cloud can become the connectivity between our remote enterprise, our remote factories or remote devices that we're trying to control, and they can be globally, anywhere in the world. So what other kind of things could we control? And so we're going to talk about some additional use cases, and I think Mark's going to take over and do the first set of these.
Just very quickly talking about some other potential uses. If you go back to the original story, we had multiple vendors supplying the matching cylinders and pistons. So here's where we can have that exchange of information between the various different companies to make those matched pairs. The second one I think is my favorite because it starts with autonomous driving, thinking about the futures. Was it 2-3 months ago, there was a company called Otto that had a partnership with Budweiser, and they did their first autonomous truck delivery of Budweiser beer down in Texas. That's my kind of autonomous driving. So picture, if you will, the autonomous truck pulling up to a potentially autonomous warehouse where they do the assembly. So we can use something very similar to these types of components to make sure that the truck goes to the right dock. The door opens to the right level to match the back of the truck. The level of the dock height matches the back of the truck for the delivery. All that being done through sensors and controllers just like this. Another case here is think about rooms, like if you're building chips or you're building silicon chip type things. You'll need climate-controlled facilities, so you can use very similar things like this to make sure that the pressure of the air is where it needs to be. You can cool coolant towers to make sure that they're available to keep devices nice and cool. So it can be used to control HVAC systems and all of that. And this is all being done through the Spring and GemFire and Cloud Foundry, the gateway that we spoke about. Okay, Larry?
And a couple of different additional use cases example would be material handling control systems. In material handling, that's usually some form of, like in a baggage system or a package system, you have conveyors with diverters that route the box or bag or whatever to different conveyors to move it to the proper point. Like, what if you need to find particular specific bags, and you want those bags, instead of running around trying to find them, you want to tell the system, pass that data down to the low-level controllers, hey, this barcode, I want that one diverted to this location. Then using a gateway like this, you could pass that information from which typically you would have the person and their barcode up in the enterprise, pass that down to the low-level controllers that are controlling the conveyors and the diverters to send it to a specific location. Then using the gateway, we can pass that information from the enterprise to the lower-level control system. Another application would be if you've got cooling towers or any type of compressors and things with cooling fans on them, And you could then utilize, if you've got variable frequency motors, drives on them, then you can control the speed of that so that you run that cooling fan only at the level that's needed to move the amount of air that's appropriate for that given environment temperature and humidity levels and things like that. Enabling the gathering of data directly from sensors and devices. Now, this would be possible if the response that you need is not in milliseconds. If you're measuring temperature on something that's got large heat capacity, or you're measuring levels in tanks that have large volumes and the level doesn't change that often, then it's possible to go direct from the device. You could connect the device directly to the PLC so that you could read the I/O, and then communicate that up and send it straight up to your enterprise. Where in the enterprise we could be determining what those levels should be or what those temperatures should be of these particular physical devices. Another application is with just-in-time manufacturing. Most lines now do not run a single product. They run many products on a given line. So the line is reconfigured. An example would be like case packers. Case packers, we have rails that we align the parts, and then we have pushers that stroke to push those products into cases. Well, we may be running many different box sizes or whatever. So that case packer, based on the product we run in, has configuration program that tells it where to position the rails and how far to move the stroke on the pusher. Right now, in most situations, those programs are maintained at the machine, which is an issue because people make changes to those programs. And then you have no way of determining when that change occurred. By moving those programs and storing them up in the enterprise, then we can control changes to those programs, to those configuration programs, and then download to the machine the program that's applicable for the product that we're going to be running, so that the machine has the correct configuration. Another issue that typically this runs into is the amount of memory in the controllers at that lower level is limited. So when you start talking about a significant number of programs, that can really be a real issue because most recipes on these machines, you have to designate the amount of memory for the largest program that you're going to store. So that means you're limited on a number, where in the enterprise we have, pretty much unlimited amount of storage space. Oven temperature control. I want to talk about this in a minute. And I know this because I've worked on this. In automotive assembly, when they get ready to put a harness in an automobile, they want that harness to be heated so that it becomes supple and pliable. So they put those harnesses in bags, and they put them in ovens, and they run them through these ovens, and they want those harnesses at a given temperature when it comes out of that bag to go in the car so that they get nice round radius bends with the harness. So when they put those harnesses in that oven, what happens if the line goes down? Those bags can stay in there too long and overheat. So the enterprise knows that when the line's running, it knows what the production capability, what the rate's going to be of production. So by using a gateway, the enterprise can send down to the oven, and you can adjust the temperature up and down on the oven based on the dwell time that this bag's going to be in there, so you don't overheat these bags. Another application would be like controlling the level in silos, material silos, or chill water. Most companies that use chillers, they run those chillers at night when they have the least power usage to balance out their power usage. And they store it in underground swimming pools. And so basically, the enterprise knows what the next day's production levels are going to be. So it knows, and it knows what the forecast temperatures are, so it can calculate the amount of chilled water it's going to need so that you don't overproduce chilled water and have that amount of water. These are just some managing power usage. Whenever you start up any type of large industrial application, you are always concerned about the starting and the peak power usage. So you want to start things up in a very defined order with a very defined spacing of time. And that is so that you keep your power usage down. And that would be another application where we can pass down from the enterprise when to fire off each of these start up each of these motors or whatever, start up an oven or whatever. That would be another typical use case. Now, the thing that I want to point out here is that we're not talking about replacing people's existing control systems. Most of these control systems were built by the OEMs. And there's a huge amount of liability anytime you go in and start changing these control systems. So but we want to enhance the data that we can pass down to that control system. So that's where this gateway solution comes into play. In that, like in these PLCs, we can wrap the program and we can pass in the control parameters at the beginning of the program and extract data out at the end of the program and never affect the actual program itself. And so this gives us a way to now connect into those low-level controllers that controls the physical world without a huge amount of liability. If anyone is interested, I will be glad to share any of this code with you. There's my email address, and send me an email and I will give you direction on how to set it up. And like for the PLCs, you're going to need some application to actually be able to load the program, and I can get you set up on that where you can get that. That's actually a free download, but you'll need to know where to go and how to get it set up. So if you're interested in any of the code, please send me an email, and I will be glad to share any of it with you and explain to you how to get it set up and running.
Okay. All right. Thank you very much. That ends our presentation. I appreciate you sitting through and enjoying, hopefully.
Is there any questions? Anyone having questions? Right. Right. Well, that would be dependent on your networking. You're talking about what kind of... Well, you're talking about the NIC, how fast I can communicate with the lower level. Typically, I can communicate sufficiently at around 50 to 75 milliseconds. I can send messages at 50 to 75 milliseconds. I can send messages. Yes, I've actually had this running on a machine. I did back about a little over a year ago. There was a traveling head die cutting press, and they lost the control system on it. and there were no replacement parts. And the issue is that everyone who has tried a solution, they were trying to do the entire solution in a PLC. And they had lost the ability where I mentioned about having configuration files. Well, with a traveling head die cutting press, you have a control program that defines the cuts. And you can have hundreds or thousands of these programs. And so what we did, we implemented this solution where we used the IoT Bridge and stored the programs, and then when they got ready to run that particular die, we loaded that program in, but we still did all the machine control with the PLC. Yes, it's actually in production.
Can we use MQTT? Can we use MQTT TCP?
I haven't done that, so I've just only used TCP and UDP. Okay, is there another?
No, I think let's clean up. And
Okay.
Because there might be, I don't know.
If
there's
anyone
another
has any
presentation.
questions, like to discuss anything, we'll be glad to stick around and discuss it with you.